Welcome to everyone to our FAIRmat tutorial number 15, the title of which is Use of Pinex Tools with Examples from Optical Spectroscopy. So this tutorial, number 15, is given by Heiko Weber, that's me, Sándor Brockhauser, Ron Hildebrand, and Chris Sturm. We are all from the FAIRmat consortium. I will explain this in a minute. And here's an outline of the tutorial today. So we start at 1 o'clock and are slightly delayed because we waited. My name is Heiko Weber. And then I will just give an introduction to FAIR data management in a very general way. Then we will talk about Nexus data modeling. This is presented by Sándor Brockhauser, another half an hour. Then there will be the core of this tutorial, a hands-on part made by Ron Hildebrand about data conversion and verification using Pinex tools. This will last for about an hour, so that the dates are not sharp. We will try to be roughly in time, but sometimes it's hard to predict also. And then we will have a half an hour presentation by Chris Sturm about data, how to handle data in NOMAD. Okay, let me start. To introduce myself again, my name is Heiko Weber. I'm professor for experimental physics, solid-state physics, at the University of Erlangen in Germany. In a side job, let's say, I'm also working for and with FAIRmat in order to organize research data management, and I'm FAIRmat's speaker for the experimental section. And here's an outline of my 30-minute presentation. I will introduce the FAIR data and the FAIRmat consortium concepts, then talk about a workflow for experimental data in a very general sense and about further action, like 30 minutes, as I said. So let's start. The traditional part here on the left side, how to handle research data, is this one. And I'm focusing on the experimental part. Let's say for theory, it's similar. So if we do an experiment, we are planning the experiment. This sometimes lasts like 2 years or sometimes just a few minutes. But after all, there's a planning phase. And then we do the experiment itself. And in a physical experiment, we collect data. Okay, so this data collection is the essential part of the experiment, I would say. But after this, we typically have the data and we have to worry about how to interpret them. We have to do analyses. We have to convert the data, to filter the data, to select the data. All this analysis is an important part of our science. And in the end, we will publish the results. So this is the old the old way of doing it. And after all, what remains with what happens to the data? Typically, they are stored somewhere, either on a directory in your institution or on a CD. And after some years, no one will ever understand the data that you measured. Now, this is the old style, and we are about to convert our science in this new data life cycle, where we start again with planning and do the experiment like data collection and then do the analysis as well. But then we worry about how to preserve the data. Okay, so we store the data in a place where we can work with it, share the data and so on. And the idea is that we share data with others. You know, instead of only publishing the paper and the message, we share the data. And finally, people can reuse them and reinterpret the data and compare them with other measurements, with other experiments that are done, and so on and so forth. And then a new cycle may start where people, based on data, not on their own experiments, but based on data, make their own science with it. That's the new data life cycle. This is where we are heading for. Well, this has goals, obviously. Or if we talk about research data management, this is how to organize all this. This has goals, and there are 2 goals, actually. If you talk to the people, the first thing they say is, well, in my lab, data should be organized such that I, can efficiently reuse the data. Because, as a university professor, I can tell you when the people have left the university, it's hard to cope with the data, to understand what has been measured 5 years ago. So your lab should be organized such that you can efficiently reuse your data. This would be a true benefit. But there's a second goal, and this is on the worldwide scale. not only your group, but the whole world should benefit from the data. And that's the far-reaching goal, I would say. There's no conflict between these goals. You have to prepare your data such that not only you, but all the others can understand it as well. There are underlying principles for organizing this, and they have been nicely formulated in this paper in 2016. And they are called the FAIR principle. FAIR stands for findable, accessible, interoperable, and reusable. And this is actually easy to understand in its rough principles. Data should be available to the people, so they should find them. Either by Google or by a link, they should have access to the data. And not only finding them, but having access, as I said. So this could be behind a login or whatever, but there should not be a hurdle like you have to ask somebody to get the data. The third part, the I, stands for interoperability, and this is the hardest one. Why? Because we want to have the data such that you can compare my data sets with those of other groups, say in a different country, and in order to make joint information out of this data, to make them interoperable, you need a community agreement. So you need an agreement how to store the data such that you can compare. And the final purpose of this is the reusability, so having benefit from the data. Now, some people rephrased this FAIR acronym and said, well, FAIR could also stand for findable, that's the same, and artificial intelligence ready, because this is what it's all about. In a year from now or in 10 years from now, there might be people crawling through all the data that have been made in a selected field and compare them and have new science out of it. And we should prepare for this. So this is a larger movement that started virtually, say, 20 years or 25 years ago. And it's sometimes called open science, open data. And we are all aware of this open access movement, which started in the year 2000, before publications were printed and were in the bookshelves in the libraries, and only few people in the rich countries, say, had access to them. And now we have the system of open access, peer-reviewed literature, where everyone has access within seconds to this and in an electronic way, which is a big advance, and this is why it's enforced by funding agencies as well. The FAIR principles have been stated, as I said, in 2016, and there was an immediate confirmation by politics. So at the G20 summit in China in 2016, all the leaders of the Western world, say, committed themselves that research data should be stored like this. There's a European strategy that emphasizes the importance of data and also research data as an important resource of our wealth in the European Union. And there are today expectations. So the Deutsche Forschungsgemeinschaft and other funding agencies expect fair data from us researchers. And this means if you want funding, then you have to deliver fair research data. But moreover, beyond this political will, there's a growing interest, and this changed a lot in the last, say, 2-3 years, that we have now a demand for good data. So the scientists request high-quality data sets in order to establish data-driven science, in material science, in medicine, in many other disciplines as well. And this is why in Germany there have been the NFDI consortia being formed. This was a call for consortia a couple of years ago, where over all disciplines in science, like humanities, life sciences, engineering science, and natural science, consortia have been created that try to organize in their fields, bottom up from their fields, how to organize research data. And for solid-state physics and materials physics, the FAIRmat consortium, so our FAIRmat consortium, is the one that deals with organizing research data concepts in our field for condensed matter physics and the chemical physics of solids. And here we are. This is just a group photo. It's a consortium within this National Research Data Management Infrastructure Scheme. We are about 60 principal investigators, so scientists, and about 30 central co-workers. Many of them are coding and trying to organize concepts and also tools for organizing research data. The spokesperson is Claudia Draxel, and Christoph Koch is the deputy spokesperson. So an excellent group of people. And we are all belonging to this group. So we should understand FAIRmat. FAIRmat is this consortium that builds this federated data in for solid state physics and material science. So we are organized as a consortium in several areas. We start with synthesis. This is about how to fabricate materials and all the data related to it. There is this section experiment that we belong to. We organize how to characterize and how to understand materials and all the physical relations. So we try to understand or to organize research data management for experiments. There's the important branch of computation. I will explain this in a minute, and infrastructure. And the infrastructure I will explain in some more detail, but there's also use cases, training, and coordination. So it's a consortium that is well organized, I would say. But let's talk about this infrastructure. So core of our FAIRmat concept is a common service that we call NOMAD. And NOMAD is a web-based service for fair research data management. So the idea is that you can do all this that I displayed, like publishing, working with the data, analyzing data on a single platform, and NOMAD provides this software solution for doing so. It's under development, but I will introduce it from its historic part. So in order to understand NOMAD, it's good to go 10 years back in 2014, where the NOMAD repository has been launched as a service. It was called at the time the Novel Materials Discovery Laboratory. And the idea was to provide a server, a repository, where you could upload all sorts of computational material science data, like density functional theory data. No matter with which software it was created, you could upload it. And then it was, not only collected, but also made interoperable. And this has developed pretty well. Now the new logo is this one, NOMAD, Materials Data Managed and Shared. We have today the situation that we have about 13 unique visitors per month, accounts from more than 1,000 academic institutions, and you see worldwide coverage of this. About 15 million uploaded entries, not only theory data at this time, and about 3.4 million represented materials. So a big success story. And I would like to highlight that this was done before the word FAIR was even invented. This is the FAIR concept implemented for this sort of data. And in order to give you just an idea of what you can do with the data, there are all these data that are uploaded. And if we click, for example, on zinc and selenium on the periodic table, we can find compounds that contain of zinc and selenium and others. For example, this one, where you have a zinc, selenium, potassium compound that has been computed. You see the crystal structure, you see lattice parameters, you see the band structure, density of states, and also the prima zone with reflects obviously the symmetry of the compound. So you can really look at all these data and find them. And moreover, you can grab into the data with an API and compare and work with the data. Okay, so not only looking at them, but truly working with it. And this explains this thing. If you publish it, so if you give it to NOMAD, you can not only explore all these results, but you can also analyze and compare them with artificial intelligence tools and many more, which lead again to science and to publication. Okay, NOMAD can handle various data formats, provided that a formal schema is available. So not only you have to deliver your data, but you have to explain how these data should be interpreted. And this is a very important part of it, the schema. And Shandor will talk about the schema for experimental physics in the next presentation. So NOMAD is already now a performant platform for big data studies of computational data. This is where it comes from. And selected experimental applications. It can also be used as a highly structured electronic lab notebook. This I will explain in a minute. So actually, I mentioned the goals of research data management. First, I would like to organize my own lab or your lab, and second, worldwide access to it. And for this, we have NOMAD coming in two flavors. So there's this worldwide repository that I already mentioned, the NOMAD repository, but it has a local copy of it, the NOMAD Oasis. It's just the same software running, could be on a laptop or in my lab in the computer center of my university, and then have local access to this functionality. So here I can organize the research data from my group or from my institute And then, if desired, I can copy these data to the NOMAD service, to the worldwide service. Okay, these two goals are independently addressed, but basically by the same software. So far to FAIR data and the FAIRmat consortium, let's talk about a workflow for experimental data. Well, experimental data are significantly more complex and diverse as compared to theory data. And this is why we have focused on 5 different techniques. One of them is optical spectroscopy, and today we will emphasize on this. So if you want to structure the data in this, say, web form, like here, registration for a conference for simplicity, then you can say, well, I register, I have this element and that element and this and that. So this will probably not work for experimental data. Why? So here it's not adequate, just filling out a form is not sufficient because experiments are so diverse and so complex that you cannot simply find these assignments to a simple web form. We have to have something more complex. And if we look actually for experimental data, we have the following scheme running. We measure something, so we create the raw data, but there's more than these raw data that we collect. We have the metadata. And metadata is all the data that explain actually what has been measured. It explains the details of the measurement, what has been measured, which sample, when, under which conditions. All this is metadata, and obviously the metadata are an important part of the data. The same is true for the data analysis that we often perform after the measurement. All these scripts, all these filters that we apply, they are part of the data. And all this has to be collected to the entity of structure and structured to the entity of data, which involves also the metadata. And we have to structure this along a data schema. And this is what we are talking about today. We have chosen to go for the HDF5 format, and because an HDF5 format is just a proposal, we are not forced to this. Can you see it? No, you can't see it. Sorry. Now I've made a mistake. But let's move on this. We will see the HDF5 format later on and the Nexus standards. So this is a file format that connects, data, like the data themselves and the metadata, like in a directory on your shelf. We will see this later on. And the Nexus standard, we will see in a minute what it is about. So the idea is that the data should contain all the relevant information and not a web form or a database like the web form I presented beforehand. This would be too easy. The data should speak for themselves somehow. And for these Nexus standards, so the structure of the data, we have chosen to elaborate further the Nexus harmonization scheme. So harmonization means we want to have the data structured along some agreed upon standards. And Nexus is a schema that has been developed about 30 years ago, a 30-year-old description schema for experiments, and it has been created in the realm of electron, neutron, photon beam communities, so synchrotrons and these things. FAIRmat contributes most actively to the new standards within Nexus and actually expanded the capability of Nexus far beyond these electron, neutron beam communities in the past years. So the idea is that we harmonize or pre-harmonize the experimental data such that the data have already a very, reliable and community-agreed structure. This will be explained in more detail by Sandor Brockhaus in the next presentation. Well, once we have this data structured like this, or similar, okay, but when they have the Nexus standards and this HDF5, for example, we can immediately pump them on NOMAD because the data schema is then available and NOMAD will immediately understand it. And once it is in NOMAD and understood, you can now work with the whole capabilities of NOMAD on it. So you can search your data, you can do visualizations, you can do analyses, for example, run Python scripts or Jupyter hubs on it. And you can use it as a repository to finally publish your data. So all this on the same platform, NOMAD. And here's how this may work for the example of photoemission. We will see it today for the example of optical spectroscopy, but to see that, that this is available, this concept is available for many techniques, I've chosen photoemission workflow. And there we have the situation that you collect with a detector actually data, which we would call raw data. But along with this, there's a lot of instrumental metadata, like the temperature, the vacuum conditions, and so on and so forth, and all the settings of the instruments. All these are the data that are formed. And we want to store them along a schema. So we want to have the data structured. And here we take the Nexus base classes, actually, which provide words how to sort in an experiment. Like, how can we describe the beam? How can we describe the data? And we need categories where all the information is sorted in. So there's a lookup dictionary. And in order to have an application later on running, like we want to do something with the data, we have to define what should be actually there in the data. If you want to work with band structure data from photo emission, then you have to provide a set of data such that you can calculate this band structure. And these application definitions specify what data should be in there. You know, what information should be collected out about the beam and the detector and that and that. So once this is available, the data and the schema, we can feed it into what we call a parser. It's then a Nexus file. It should be checked for compatibility. And finally, it's in NOMAD. And in NOMAD, you can then perform analysis with it for photo emission. There's a lot of functionality that you can do, like project it in the band structure on different directions, or do peak fitting, voxelwise Fourier transform, and so on and so forth. So a lot of analyses are available on the NOMAD platform. But we look today at the wave of the data from here to here, and we organize this by the PyNext tools. This is what this tutorial is about. It takes the data from the raw side, say, and pumps them in a structured way, finally into NOMAD. Okay, let me emphasize, I have a few minutes left, that this is not everything we do. We do even more, and these further action are briefly highlighted here. So if we talk about experimental data sources, we can, in rough terms, split it in two parts. One is we purchase a machine in material science or physics that does a job, and very often such a machine, like here, a scanning electron microscope, has its own form of data formats that it brings along. So vendor provided software and their own standards. Okay, and this is hard to cope with. It's often not open source and hard to understand what has actually been stored. And that's the second case, and this is home-built experiments. Like, from many decades, there are instruments, they are all collected, and a PhD student writes the control software and has its own output format. And this is also very heterogeneous. Okay, and if there are 100 students, there are 100 different output formats, how they are put out. How can we cope with this? Let's focus first on the instrumental part. And here we have a process that we call the technology partner approach, where we actually try for these fields here to formulate in a community an agreement how the data should be stored and approach to manufacturers, and by bringing in a workshop, scientists, manufacturers, and our data experts together. If we have a good concept how data should be stored, they are typically willing to do so, our technology partners. And we are now in a process for different fields where we try to convince the technology partners to store along the Nexus format. And surprisingly, they are willing to do so because they understand that we as scientists need, highly structured data, and they support us, obviously, as our clients. So with this, we need the help of the technology partners, of the vendors. Here we are organizing, our students somehow, and here we have also a solution to offer, and this is the Camels concept. So Camels is a software that we developed in FAIRmat, and it's actually thought to be a service to the user. The user interfaces with Camels just by a graphical user interface. And then the user can define an experiment or a measurement like this. Typically, a measurement follows abstracted commands like first initialize the system, then set these and these values, then wait a little bit and read the data, and then make a loop like sweeping data back and forth and so on. So with Camels, it's sufficient to configure this measurement protocol rather than writing software. Okay? This is extremely efficient because Camels takes over all the communication with the instruments for different categories, old and young and everything experiment. But the big point about it is that we control the output. So having all this information about the instrument, we can simply write it down in a structured way. in the way we need it for FAIRmat and for NOMAD to understand it. So we have the raw data, but extremely many metadata, including the device settings, protocols, and so on, everything that can be collected electronically. And the output is again structured in an HDF5 and Nexus similar format. Okay, so this is a service for everyone who tries new experiment. Try it out. It's actually fast, easy, and gives you a very well-structured output. So last slide, instead of a summary, I would like to say, well, how do we store our data in the future? Well, we store them FAIR. What else? Okay, FAIR data, what else do we need for the future? We want to pave the way, actually, for data-driven science in experimental solid-state physics and material science. And the advice to you is structure the data, upload it to NOMAD, and then you can work with the data like never before. That's my final slide, and I hand over to Sándor Brockhauser.